Welcome to the course on plasma physics and applications. Today we will discuss the regime that we refer to as the burning plasma regime and the role of fast ions in it. We will start by defining what a burning plasma is and by highlighting its specificities. We will describe the fast ions and their role in the external and the self-heating of the plasma. We will then look at the losses that fast ions can be subject to because of a number of reasons: inhomogeneity in the field, low frequency plasma modes, turbulence, or resonant interaction with alpha waves. We'll then say a few words about the stability of the burn and its control. I would like to start by reminding ourselves about the DT fusion reaction, the one we'll use for ITER and the first generation of reactors. As we have said already together, we have a tritium and a deuterium ion that fuse, producing a neutron, a 14 MeV of energy, and a helium nucleus at 3.5 MeV of energy. That's an alpha particle. The neutron has two jobs. It will react with the lithium-6 that will be present in the blanket to produce the tritium that we need for the reactions themselves. And of course it will be used to heat a fluid around the plasma that will be used to generate electricity. The alpha particles has one single task for us, which is very important. It has to be kept in the plasma and heat the plasma ions in the core so that they maintain reactivity. We call that the plasma self-heating. So what is a burning plasma? Let's recall the energy balance. We have a possible variation on the energy content in the plasma because the alpha particles heated, if we have fusion reactions, or because we put power from the outside, so-called additional or external heating. And of course, with the minus sign, we have to include the term for the losses that we have said in the past being dominated in general by direct losses, represented by a single parameter, which is the energy confinement time. Let's express the fusion energy gain, capital Q. That's the fusion power divided by the input power. And because the alpha power is about 1/5 of the total, we can write that that's about 5 times the power in the alpha particles divided by the input power. So if we are interested in the heating fraction that comes from the alpha heating fraction F alpha, which is the power in the alpha divided by the total power, that can be represented in terms of a very simple expression containing Q. That's Q over Q plus 5. So the experiments we have performed so far have reached a Q of less than, say, about 0.7, which corresponds to an alpha heating fraction of less than 12%. So really the alpha heating term is subdominant compared to what we heat the plasma with from outside. Even if we had reached break-even, which corresponds to Q equal 1, the alpha heating fraction would be only about 17%. So the limit, of course, at which we start to have a different regime is Q equal 5, because at Q equal 5, we have an alpha heating fraction of 50%. So what goes on, starting from that value of Q to higher and higher value of Qs, is what we call the burning plasma regime. This is a burning plasma regime because the plasma, in a sense, is dominating its heating by its own byproducts. Of course, the limit is exactly Q equals 5, but if you have Q equals 10, we have an alpha fraction which is about 67%, going all the way to 100% when we reach ignition, at which point, of course, the gain goes to infinity. We don't have burning plasmas as of today, so we can only speculate on what their specificity would be. First of all, of course, we need to reach high performance. So burning plasma would be, sort of by definition, a high-performance plasma in a tokamak reactor. It would be close to the operational limits that we can have. If we have very large heat flux on the plasma-facing components, as large as you can cope with generally. It would be a nuclear environment, something we don't have again today. There would be a lot of radiation involved. There would be the issue of the retention of tritium, for example, in the first wall of the tokamak. There would be the issue of a dust production that contains tritium. There would be the issue, of course, of the need for breeding the tritium using the blanket modules outside the plasma. In terms of the plasma physics specificities, also, we expect something different from today for a few reasons. First of all, it would be very high density and temperature compared to what we have today, which implies we are in a regime where we have even lower and lower collisionality compared to what we have today in present devices. And perhaps even more importantly, in terms of basic physics, we have a very small ratio between the size of the plasma particle orbit and the size of the device. And this is not just a detail. This implies that the turbulence, for example, that can develop in a system in which the particle trajectories are much smaller than the typical length scale of the system could be very different. And of course, last but not least, we'll have a very large isotropic population of alphas, which will be, again, by definition of a burning plasma, the dominant source of heating. This will imply that there will be a coupling between the profile of the alpha power, the profile of the pressure of the plasma, the safety factor profile, and the profile of the electric field, the profile of transport parameters, profile of the concentration of helium, and so on and so forth. So all these elements will be coupled in the burning plasma, whereas in today's experiments, they are all completely, or at least partly, decoupled from each other. These are the main elements that we need to achieve, study, and issues that we need to solve to get to the burning plasma and to control it. First of all, we have to reach the burning plasma conditions, of course. So we need to identify which heating scenarios, for example, we can have in approaching the burning plasma conditions. We need to understand what the transport and turbulence behavior would be like in these conditions, and in particular, what would be the effect of different isotopic masses in the plasma. We know that there are differences in the transport that we don't fully understand between, for example, deuterium and tritium plasmas. We need to learn how to sustain the burning conditions. We need to really make sure that the self-heating process is not affected by any major instabilities or any major problem that can arise in the plasma. And among the problems that we have to worry about are the losses of the fast ions that, of course, those that guarantee the self-heating process in the form of alphas produced by fusion reactions. We need to see if the stability of the plasma is affected by the presence of fast ions and in which way it is affected. We also need to have a thought on the stability of the burn and how we control it. Now, thinking about the reactor, we need to make sure that the conditions for the plasma to burn are compatible with the operation of a reactor from which we want to extract energy. I'm thinking about the interaction between plasma and the wall, the exhaust of power and particles, how we get rid of the helium ashes, for example, in particular, helium ashing being the essentially the alpha particles that have given up their energy by collision and that we don't need anymore in the plasma. We need to worry about the heat loads, the high recycling regimes in which we have a lot of particles are re-injected in the plasma due to the interactions between the plasma itself and the walls, operating with a large fraction of power that is radiated out from the plasma, how we can mitigate disruptions and other violent events at the plasma edge, such as the edge localized modes that we have investigated briefly in a previous lecture. We have to worry about the retention of tritium in the walls and avoid or limit the production of dust. We also need to see how these phenomena can be extrapolated and what they imply for the operation of a reactor. We need to worry about breeding tritium, which is a very important element for the economy of fusion in the future, how we can burn tritium efficiently, and the thermodynamical efficiency of the reactor itself, for example, giving some constraints on the operational temperatures for the reactor and so on and so forth. These are many, many elements that one needs to look at for a burning plasma and for a reactor to be compatible with a burning plasma. Now, we don't have the pretension to really investigate all of these in this lecture and in this course. I'd like just to give a few highlights about the specific chapter in which we discuss how we can sustain the burning conditions. So we look at the self-heating process, the fast ion losses, the stability of the plasma in the presence of the fast ions, and we say just a few words about the control of the burn and its stability. So why are fast ions so important in the plasma external and self-heating process? I remind that here in this sketch, we of course here have the plasma in which we inject power from outside, and we have reactions that produce alpha particles which carry about 20% of the energy which must be kept in the plasma, and the neutrons that come out of the plasma with about 80% of the energy. So the loop works as follows. We heat the ions, they fuse, they produce alpha particles, and therefore a significant alpha particle power, which will therefore subsequently given by the electrons via collisional processes. As we have seen when we discussed the neutral beam injection heating method, if the energy of the fast particles is very large, the collisional process will first give this energy to the electrons rather than to the ions. So this is why I have represented this loop as the collisional process giving energy from the alpha to the electrons, which in turn have to thermalize on the ions. So it will be sort of an indirect heating of the ions via the electrons. This is if we count on the alpha particle heating, but similarly we have the same situation for the fast ions if we count on ICRH or NBI, because in those cases you produce fast ions, they will then, again, depending on the energy, giving energy to the electrons or directly to the ions. So fast ions are very important in the process of heating the plasma, both from external sources, at least for ICRH and NBI, and for the self-heating via the alphas. And this is just a sketch. This is sort of what we hope the fusion process will be like. We count on the alphas slowing down collisionally on the background electrons and ions. But is that really happening? A number of experiments have been performed to verify that. And take one example here to check that in a simpler situation, that indeed is the case. Here we see the result of a trace tritium experiment in jet. Very small amounts of tritium are injected in a deuterium plasma with blips of the neutron beam injector, in which we put tritium. So what we cause are DT fusion reactions between the tritons injected by the beam and the plasma, which contains deuterons. And of course, these DT reactions produce 3.5 MeV alphas, just like any DT reaction. What we're looking at in practice are the emission profiles of gamma rays, which are issued from the reaction of the high energy alphas with beryllium impurities that are present in the plasma. Now, the interesting property of this reaction is that it's a threshold reaction. In other words, it happens only if the alphas have a certain energy, typically above a couple of MeV. So the emission of gamma rays is a signature of the presence of alphas with an energy that's about 2 MeV or more. We can therefore take the decay time of such an emission, or in practice, the decay time of the measured radiation in the gamma range of frequencies, to get an estimate of the slowing down time of the alphas and, of course, of the beam tritons, slowing down time that is supposed to be given by the interaction with electrons. And that's what we see in this plot. This is in the vertical direction, the decay time of the gamma radiation as a function of the calculated slowing down time according to classical theory. And we see that in a situation which we have a few megaampere of current in the jet tokamak, and the magnetic field between 2.2 and 3.5 Tesla, around that, we have a very good correspondence between the two typical characteristic times. So in these plasmas, which are quiescent, so we don't have any major instabilities present, the slowing down that we observe indeed follows classical theory. So everything seems to work according to what we expect. If the alphas slow down collision on electrons, as classical theory predicts, we should see, from the point of view of electrons, an increase in the temperature, because the power from the alphas goes directly to the electrons. And that was the purpose of two very significant experiments in TFTR, the tokamak at Princeton, USA, and in JET. First, in TFTR, the electron heating by the alphas was seen quite clearly, comparing a deuterium-only plasma, which is in blue here. This is the profile of the electron temperature, with a very similar plasma, but in which there is a 50-50 mixture of deuterium and tritium. And you see there is a significant difference, or at least a measurable difference, between the two profiles in the presence of a DT, which means in the presence of alpha particles, there is a heating by the electrons. If we take the difference between the DT case and the pure deuterium case, this difference appears, of course, in a much more clear way. And you can see that that difference occurs more in the core of the plasma, where the alpha particle power is deposited. Similar experiment was performed at JET as well. Here we plot the results in a somewhat different way. Is the core electron temperature as a function of the alpha particle power from the fusion reactions. And we can see that we have different mixtures of DET indicated in the brackets here, from 0% to, say, around 50-60%. Of course, 0% or even close to 100%, the effect is zero. In a sense, there is no heating of the electrons because of the alpha particle power, because there is essentially no DT reaction taking place. The optimal situation is that close to 50%, where we have about 1.2, 1.3 megawatt of alpha particle power, and that results in a very clearly measurable heating of the electrons in the core. So alphas are doing their job. They're slowing down collision on the electrons, and they're giving their power to the electron channel. So why do we have to worry about these self-heating processes or external heating processes? Well, the question is whether that collision or slowing down is always happening in the way we hope it would happen, as we have just seen in the two very simple situations in that there were no major instabilities, no major perturbations to the quiescent plasma. What we worry about is if we have fast ion losses for different reasons, that they will influence the power that will be transferred from the alphas to the electrons, as well as the power that will be transferred from the fast ions issued by collisional, by additional heating. In this case, power can be transferred to the electrons or to the ions depending on the energy of the fast ions. But in all of these cases, if fast ion losses are present, this transfer will be affected, and therefore the plasma will not be heated efficiently. So what mechanism can we have to lose fast ions in an actual tokamak plasma? First of all, we worry about fast ion losses that can happen because of the three-dimensionality of the magnetic fields. In a practical situation of a tokamak, the number of coils is of course finite. So if I go around a torus, being a charged particle, I don't feel a completely uniform magnetic field. I will feel an inhomogeneity in the intensity of the field. Just below the coil, of course, it will be more intense. In between coils, it will be weaker. And as a charged particle feels inhomogeneity in the magnetic field, it can be subject to trapping. And if particles is subject to trapping, it will not go around the torus. It will not feel the field of the tokamak that we have set up so carefully to compensate the various drifts, and therefore get out of the confinement region, being trapped in between coils and then drifting out, providing direct losses. These are the so-called ripple losses, because they are caused, once more, by the inhomogeneity of the magnetic field due to the number of coils that's finite, which can be simply called the ripple of the field felt by the fast particles in motion around the torus. This is something that can be calculated fairly accurately. An example or remedy for a particular scenario in ITER is illustrated here. One can actually insert ferritic material, so high mu material, to smooth out these variations and reduce the losses significantly. This kind of solution is already foreseen for ITER and even considered for the steps after ITER, but there's still a few open issues that one needs to address. And one of them is the effect of the blanket modules, which contain ferromagnetic material, therefore possible perturbation to the field structure. Blanket module is, of course, necessary for tritium breeding. Fast ion losses can also happen because of low-frequency magnetohydrodynamics modes. There are many modes that are possible. We'll illustrate a couple of examples. In general, different kinds of resonances can be associated with the complex particle orbits and lead to different possible interactions. This image that we have seen in previous parts of the course illustrates the complexity of the orbits in a tokamak for ions, for example. Of course, you have the fast gyro motion around the field lines, which is associated with the cyclotron frequency, and that's one resonance. But now we consider much smaller frequencies, much slower timescales. Now we have seen already that the motion of the ions around the tokamak is actually characterized by what we call banana orbits, which are orbits that are produced by the fact that the particles feel regions of different strength in the magnetic field and therefore are trapped. And the turning points of this trapping motion are related to the in-out asymmetry of the field. If we project these orbits on a poloidal plane, they look like bananas, so they refer to them as banana orbits. And if we look at the motion of the particles along these orbits, if we see again in the poloidal plane, the particles will go around. So there will be a frequency associated with this motion around the banana orbit. And that's one of the frequencies that we can have coinciding with the frequency of an instability. And of course, when the frequency of a motion of a particle coincides with the frequency of an instability, you can have very efficient exchange of energy and momentum. You can have very efficient driving of the instability. Another example is that of the so-called precession or drift precession of the banana orbits. For that, let's illustrate it with a plot from the top. So this is a top view of a tokamak. We have seen that the particle orbits can be trapped and therefore not complete a full toroidal circumference. But in fact, there is some asymmetry between the, if you like, the trajectory forward and the return of the trajectory, so that this orbit will slowly drift in one particular toroidal direction. It is as if the banana orbit would go, in fact, around the torus, seen from the top. And the frequency associated with that is the so-called precession frequency. That's slower than the frequency associated with the motion of the particle along the banana orbit itself, which is referred to as the bounce frequency. So we have, just using these two examples, two possible frequencies for possible resonances with plasma instabilities: the precession frequency of the particle drift around the torus and the bounce frequency of the particle around the banana orbit. Both of these frequencies are much smaller than the cyclotron frequency and therefore can lead to resonance with low frequency global modes of the MHD kind. And I'd like to take two examples for two of these modes. The first one is a so-called fishbone instability. It's a name that was given historically because the signal associated with the perturbation that was observed in the plasma would have a character of bursts going up, for example, in the perturbed magnetic field in the plasma. See, this is measured typically by a coil mounted on the vessel, so facing the edge of the plasma. It will go up and down with typical oscillations that will remind the fishbone shape. And that's why in this plot we have plotted on top of an actual fish. This instability is now being understood theoretically as resulting from the resonance destabilization of a kink mode inside the plasma. Resonance destabilization that occurs because the mode frequency coincides with the precession frequency for the fast ions. And the precession frequency is what we have described just 2 minutes ago. Now the point is that this kind of modes is driven by the fast ions, but in turn can reach amplitudes that cause ejection of the fast ions themselves. Now once you eject the fast ions, this was the source of instability itself. The mode will die again because the source is gone, and there will be a sequence of bursts that will occur. Each burst would lead to ejection of fast ions and therefore reduction in the core performance of my fusion reactor. Second example is even more ubiquitous. It's a so-called sawtooth instability. This is an instability that leads to a series of sudden collapses of energy and particles in the core, represented by this shape, and that's why we refer to it as a sawtooth. In this case, I represented the temperature as a function of time. When the collapse occurs, in fact, there is a local breaking of the magnetic structure, just like happens in the geomagnetic tail, in a phenomena you have seen in other lectures in this course called magnetic reconnection. This is again linked to an MHD instability of the kink type, which we have illustrated to you in previous lectures. But the frequency is even smaller than the precession frequency for the fast ions. So this is not really a resonantly driven instability in the sense of a wave-particle resonance with the fast ions. Nevertheless, the fast ions are affected by the instability because they are ejected together with parts of the core plasma. This phenomenon, in fact, is being illustrated as we speak on the little movie on the right, which shows the X-ray emissivity evolution in the TCV tokamak over a sawtooth cycle. These sudden collapses, not only are they a problem because they kick out the fast ions and the core of the plasma, or they distribute the central region of the plasma, but also they can trigger secondary instabilities. Because the fast ions influence the period of this sawtooth, which in turn determines the strength of the collapse, the fast ions can be used to control these modes and therefore to control the secondary instabilities. And this is really a very active line of research. Another possible channel for losing fast ions is the plasma turbulence. In fact, one can argue that plasma turbulence can cause transport of fast ions similarly to what it does to thermal particles. So these turbulent structures would kick fast ions out as they do with thermal ions and thermal electrons. However, we have a good piece of news here, because the fast ions are characterized by relatively large orbits, and these large orbits are expected to average out the effect of turbulence. And this plot will illustrate that phenomenon. So if you have a thermal ion which has a very small orbit, it will be influenced by, say, the electric field of the turbulence in one particular direction. It will receive a kick in one particular direction, and it will be therefore affected in its confinement and its transport. But as I increase the size of the orbit of the ion by increasing typically its energy, I increase the number of turbulent eddies or turbulent structures that the fast ion interacts with over one orbit, and therefore receiving kicks in different directions along one orbit. These kicks will therefore be averaged out, and the net effect will be reducing to zero. The key parameter in this orbit averaging effect is the ratio between the fast ion energy and the background plasma temperature. In the sense, this ratio is a proxy for the ratio between the size of the ion's orbits and the size of the turbulent structures. The second parameter that, of course, influences this interaction is how long the fast ions remain fast in the plasma, that is the slowing down time. Now, I said before that in this case we would rather find good piece of news, because if we do the estimates for ITER and the future reactors, we find out that the value of this ratio of E fast over the plasma temperature should be large enough that the turbulence effects on the NBI ions, and even more importantly on the alphas, should be negligible. I now turn to the last mechanism of fast ion losses I'd like to discuss. That is due to the interaction with Alfvén waves. So, as we said, the alpha particles are born at 3.5 MeV. They will slow down collisionally, first on electrons, then eventually on ions. And during their slowing down, which lasts a macroscopic time of order of a second, they can encounter a wave-particle resonance. So they can drive efficiently an instability in the form, for example, of an Alfvén wave, as we will see in a moment, which in turn, if it grows to large amplitudes, could give rise to losses. And the losses of the fast ions, in this case of the alphas, would of course prevent an efficient transfer of their energy to the background plasma. We have studied Alfvén waves in previous lectures. I'd just like to remind ourselves that they're coming from the following very simple mechanism. The B field and the plasma are frozen together in the frame of ideal MHD. So we can see the field lines as strings subject to tension and subject to the interaction with the plasma inertia. The combination of the tension and the plasma inertia gives the propagation of Alfvén waves. Let me just sketch that in a simple way. Say we bend the field lines, these are supposed field lines, because there's a perturbation in the magnetic fields due to the perturbation in the velocity of the plasma. See, the unperturbed magnetic field is in this direction, and we locally have a perturbation of this kind. This combination of tension and inertia in MHD is such that we have a wave that will propagate in a parallel direction to the magnetic field, with the phase velocity that will be the Alfvén speed that will be related to the intensity of the field divided by the square root of the plasma mass density, which is a measure for the inertia that's involved in the mechanism for the propagation of the wave. So as we said, the slowing down alphas, or for that matter fast ions from NBI or even ICRH, can actually resonate with Alfvén waves and therefore drive them unstable, giving energy to them. Why is this resonance almost inevitable? And the reason for that is that if I draw, say, the distribution function for the alpha as a function of time and as a function of their velocity, say normalized to the birth velocity, the birth velocity corresponds to the 3.5 MeV of energy. Say this is 1, 3.2, 0.4, 0.6, 0.8. I will have something like that as a function of time. So initially, the alpha particles will be generated at the birth velocity corresponding to their birth energy. And then they will progressively slow down. So if this was T0, this is now T1, T2, T3, T4, it's just one last one, and T5. So during this slowing down, the Alfvén velocity will be encountered because the Alfvén velocity is, or Alfvén speed is typically just below the birth velocity. So there's no way we can avoid that resonance, and that's for typical parameters corresponding to a few Tesla device, 10 to 15 keV of temperature and 10 to the 20 per cubic meter of density. The other point is that there will be potential for a very effective interaction between the slowing down alphas and the Alfvén wave corresponding to this range of velocity values, because the thermal speed for the bulk ions is much smaller. So say, for example, for deuterium and tritium, there will be something around this region. For tritium is a little smaller, and for deuterium a little higher. So there's a long way for the alphas to slow down before they reach the thermal speeds of deuterons and tritons. And during that long way, they have also a long time to interact with the Alfvén speed with which they will become resonant. So when is the wave driven unstable? Well, we have a free energy source, which is the gradient in the pressure of the alpha particles. And if that is sufficiently high, they will be in drive. And of course, if this drive will be exceeding the background plasma damping, it will be provided by a number of mechanisms in the plasma. Now we have seen what Alfvén waves look like in general and what their physical mechanism is. Without going to too many complications, we noticed that in a tokamak, the geometry of the field is such that the dispersion is modified and in fact is much more complex. But the point is that the dispersion of Alfvén waves in a tokamak still allows for very weakly damped global modes we refer to as Alfvén eigenmodes. And in fact is one of the main successes of MHD theory, one of the most striking successes of MHD theory, to predict the existence of these modes and to even predict some of the main features that have been observed experimentally and quite accurately. An example is shown here. This is a structure that's calculated for an Alfvén eigenmode, in which we have inserted, in some portions, data corresponding to measurements of the same alpha and eigenmode mode. In this case, data taken using electron cyclotron emission imaging. You can hardly notice the difference between the data and the theory prediction. So the modes are there. The modes follow the list in their main feature, the theory predictions. Do they also cause losses as we feared they would? The answer is in many circumstances they do. Losses or distribution due to Alfvén waves have been seen in many experiments. In this plot compiled by Rich Horiluk from data from TFTR, we see that the fraction of losses here is plotted as a function of the input power. On the other side of the plot, the other axis corresponds to the mode amplitude. Of course, so the larger the mode amplitude, the larger the fractional losses. And we see that for both NBI-driven Alfvén eigenmodes or isolation-driven Alfvén eigenmodes, we can have significant levels of losses. In DT experiments, very weakly Alfvén eigenmodes were observed, and so no significant losses were observed, but that doesn't mean that we should not worry about them in the future, because it was really corresponding to a very small input power in the drive, in that case in the Alfvén drive, and therefore to a very small mode amplitude range for these modes. In fact, we have to worry about losses or distribution, because in ITER and in the future reaction we can only withstand a few % of alpha losses. There is therefore an ongoing research to investigate the linear stability of the modes when they are present at all, which results from the balance between the drive to the fast particles and the damping from the background plasma, and to also see how the modes evolve non-linearly and what is the link between the wave property and the redistribution and the losses that the waves cause. Just to give you one example of this kind of investigations, this is what we study on the jet tokamak in terms of the linear stability. The idea here is that the linear stability of the mode is investigated using antennas. These are the 4 antennas installed inside the jet vessel that launch low amplitude stable modes in the plasma. The frequency of the antenna is swept, and the eigenmode appears as a resonance in the plasma response to that antenna signal. And this is a driven mode, so its frequency, of course, corresponds to the peak of this resonant response. And in simple terms, the width of the resonant response is actually the damping rate of the mode. So one can drive these modes and even track them in real time, so drive them one after the other as the plasma evolves, and extract the width of it in real time, the measurement that is of the damping rate for the mode that would be present in the burning plasma. Finally, I'd like to say a few words about the stability of the burn and its possible control. What we want to achieve is a burning plasma regime that's sustained without any major macro instabilities, any significant fast ion losses, any disruptions, any build-up of the helium ashes. In principle, a thermal runaway can occur at high fusion gain. This is represented in this plot, where the input power is represented as a function of density and temperature to achieve a certain level of fusion power, and we can see that the input power could go to 0 in particular regions of this plot, which means that we have a runaway towards ignition, which we don't necessarily want. We will lose control of the plasma burn. As we will see in an exercise, however, we have a confinement degradation with power, which means that the burn, in fact, should be globally stable. To control the burn, we have a number of possible actuators, although, as we say, the plasma is really a self-organized system when we have the burning plasma regime. We can nevertheless, of course, try to act on the heating power, on fueling of the core, on the DT mix, on the impurities that we have in the plasma, and we can in fact even manipulate the fast ion phase space distribution to optimize our burn. So in summary, we have seen together that burning plasmas are characterized by the interplay of plasma dynamics and external systems. The core of the plasma is a complex self-organized system on which we can have small amount of control. In today's experiment, we can achieve some progress on separate building blocks for the burning regime. But the coupling of all of these elements makes extrapolations from the weakly self-heated plasma we have today very difficult and may lead to new phenomena. And that's why we need to build an experiment that runs the plasma in a burning regime. This is what we'll discuss in the next lecture, and that is ITER.